In this video, we're going to expand on our basic Python knowledge, extending our use of it inside of Rhino to include functions. We briefly went over functions in the introduction video, but in this exercise, we're going to cover a couple of other properties that functions allow us to access. We can get started by opening up our Rhino interface, double-clicking into perspective, and then we can go ahead and hide that grid. Next, we can go to Tools, Python Script, and Edit. With a fresh Python script open, we're ready to go ahead and get started. We can start as always by leaving a multi-line comment using triple quotes. And in this, we can give ourselves some information about what will be contained in this script. So we'll just say Introduction to Python Functions, and I'm going to add Recursion and Aggregation. So Recursion and Aggregation, as those are two topics that we'll cover in this video. To start building a function, we first have to define it. We define a function by using the def space and then the name of the function, which we can choose as whatever we'd like. So I'm going to start with building one mathematic function called subtraction. And this is going to be a subtraction function which takes in two number values, performs a subtraction, and returns the result. So we can end this function definition just by closing that parentheses for now, and we'll come back to this. And then we need to add a colon to open up that function, hit enter, and inside of this tab space, we are going to give ourselves a comment to perform the subtraction. And then if we want to finish out some of this pseudocode or kind of language to ourselves, we can also say return the result. So return the result of that subtraction. And we can hit enter, backspace out of that tab zone, and somewhere below this definition, we're going to need to call this in order for it to run. So I'm going to leave ourselves a comment and say call function to run it. So in order to call it, to call function, use its name with an open and close parentheses. And then inside of the parentheses goes any input data that we want to pass into the function. So right now we don't have any input data being read inside of our function, and we also have no actions being performed, but we can still just structure this as though we had information already inside of it. So if I hit enter on line 11 there, now on line 13, what I'll do is I'll just call my function by its name, so subtraction, open and close parentheses. That should be enough for us to click on this gray column on the left, drop a breakpoint, and then hit debug. Okay, so it is giving us an error here, and that's just because it doesn't want this empty function here. So we do need something inside of there. So that something will just be a print statement saying running the function. We can close that out, and now when we hit play, we get information that is output from that breakpoint, and we can see that we have a name subtraction of value function subtraction. So there's actually a function called subtraction in our script, and it's of type function. So now if we go ahead and hit stop, hit OK, then we can just remove that breakpoint. Now we need to actually infill information so that it can do something else besides just printing this running function statement. So if this is a subtraction function, as I mentioned, we may need two variables to pass in order to perform the subtraction. So we can say num1 equals 12, and then we'll need another variable num2, and we can set this equal to, let's do 4. To pass this into our function, we need to place it inside of these parentheses. So if we just place the 1, then we now need a corresponding input variable going into the parentheses where we define that function. So we need underscore num1 here. And then if we want to also pass in our num2, then we first need to, where we've called it, place that variable, num2. So we're passing in that num2, and then if we come back up to the definition, we also need to take in that information, so underscore num2. The reason why these names can be different, and in fact I encourage them to be different, is so that we can keep track of what is going on inside of the function and what is going on outside of the function. And we're using this passing of data inside of the parentheses as our way to get things into the function from the kind of outside world. So we have two number variables, two integer variables to be specific, although they could also be floats. So we have one integer variable and one float variable. We can pass those number values in. We're now reading them in here. And if we want to check that this is actually working to pass into our subtraction function, we can say num1. And we can actually say equals and then finish our string, comma. And now if we were to type num1 without the underscore there, we should get an error that says we don't know what that variable is, or its reference before its assignment. So if we're just using this num1 variable, we can see that it's still printing out in our console, but what's actually happening is it's reading this variable from outside of the function, and then placing that in and printing that variable anyway. So that's why we want to use the underscore to be able to use that particular data point that is plugged in, rather than the one that we have outside. So in order to print this num1 variable, we need num1 equals, just to give us some information about that when it prints, and then we can say comma underscore num1. Now if we hit play, we see num1 equals 12. We can also, on a separate line, say print num2 equals comma underscore num2 and hit play, and that gives us num2 equals 4.7. If we want to combine these, we can just separate those by a comma as well, and it will print all on the same line. That way it just keeps it a little bit cleaner for us. So now the next step is to actually put some function or some operation inside of this function so that it's more useful than just printing these numbers. So what this is going to look like is constructing a variable result, and we're going to set this equal to the mathematical operation underscore num1 minus underscore num2. And now to check this, underneath there we can say print result equals comma result. And when we hit play, we're going to see that num1 equals 12, num2 equals 4.7, and the result, which is num1 minus num2, equals 7.3. Just to further enforce this idea of what we're passing in versus how we refer to these things inside of the function, we could even switch the order of num1 and num2. And what's happening now is num2 actually gets mapped to this first data item or first variable, which is underscore num1, and num1 gets mapped to num2. So we're actually flipping the values, which means we're going to perform a subtraction of 4.7 minus 12. So if I hit play, we now get a result of minus 7.3. This is why we want to name the variables inside of our function something different than what we have outside, so that we can actually freely pass in whatever specific data that we want to, and whatever is inside of the function does not get affected by what's outside. Because we might be doing something as kind of tricky as we just did by flipping the naming, there might be a number of reasons why we would do that that require kind of much more extensive scripts. For now, it's easy enough, but just good convention, always somehow change that name. Okay, now we have this constructing the result inside of the function. If we want access to it outside the function, what we have to use is a return. We can return data from the function similarly to how we pass it in. So when we're passing it in, we just set it in the definition here. But if we want to return it out, we need to use this return function and then pass out whatever data we want to. So in this case, our result. Now, if we just hit play, we don't see anything actually happening here. And that's because we haven't actually done anything with that information we're passing out. Now, instead, if I say print and then call that function, passing in those two values, hit play, we're now printing that result outside of the function. So if I comment out those two print statements inside of our function and then hit play again, we still see that result printing on the outside. Alternatively, we could say out equals print out, play, and we're still getting that same value printed in our console. So this is going to be the way that we pass information that we've already processed out of our function. Now, if for whatever reason we didn't want to output this result, but instead we just wanted to output one of the numbers, so you pass in a number and you give it right back. There's not much of a reason to do this, but all we have to do is change the variable we're passing out, hit play, and now it's going to read in num1, num2, still perform that operation, but just do nothing with it. And then it's going to pass out num1, which is 12, and we're now printing that value of 12. The reason why functions are useful is because doing this once, it might be easy enough, to just say here, result equals num1 minus num2, and then we can just print the result. But what if we want to maybe pass in these same variables into both a subtraction and an addition function, right? So we want the kind of options to pass them into different things. The way that we could do that is by copying this subtraction function. And then just below it, we can change this name to addition. And we can construct variables for inside of this addition function. So num1, num2. Here we'll say perform addition on two numbers. And now we just need to change that operator from minus to plus. And for both of these, we want to return the result instead of underscore num1. And now we have two separate functions defined separately, one being called here, and we can call this now sub out. And we can print this sub out. And then we can say add out equals, and to call this other function, we just call it by its name, addition, and we need to pass in some information. So we could just go ahead and pass in that same information, close the parentheses, and now when we run this, it's going to read our two variables that we've declared there. I'm going to delete this other mathematical operation that we had. It's then going to perform or call the subtraction function, passing in two variables. It's going to perform that operation inside of the function, and then return the result, which we're saving as the variable sub out and then printing here. And then below this addition function, we can also print. So then it's going to step down here, call the addition function, pass in two variable values, so two number values, which we define above. It's going to perform that addition and then return that result as well. So here I'll say subtraction, and then for the addition, we'll just make this clear and call it addition equals. Okay, now when I hit play, we get a subtraction value of those two numbers subtracted of 7.3 and an addition value of 16.7. So 12 plus 4.7 is 16.7. And the idea here is that we can do this with any selection of numbers or any definitions for numbers. So I could say num3 equals 7.1, num4 equals 11.2. Now we could change any of these, performing instead of num1 here, we could say num3 plus num2 and call this add out 1. And then we could just copy this So instead of copying this whole function every single time we want to use that, we just copy this one line and then change the variables that we want to feed into it. So we have add out to, and then we can just change these input variables. So from 3 to 1 and 2 to 4. And now we can perform the same function operation, but with two different input variables. So if I hit play, we now get the subtraction output from those two first numbers. Then we get the addition of numbers 3 and 2, so 7.1 plus 4.7. And then finally we get the addition of 12 and 11.2, which gives us 23.2. So it constructs basically these kind of blocks of code we can then call later on, which makes our code incredibly concise compared to what it would be if we didn't have this option to call a function. Another reason why these are useful, we can actually combine this functionality with the functionality of loops to iterate through certain data and still be performing this action. So what if we wanted to take number 1, add number 2, then add number 3, and then add number 4? So I'm going to delete our subtraction call here. We can leave it defined above. If we're not calling it, actually I'll just comment it out. Why don't we do that? So if we're not calling it, then it's just going to be defined up here, but Python's actually going to skip it. So we can minimize that because we don't want to look at that right now. And then I will comment out this. Actually, we'll do both of those as well. And then somewhere below, we're going to iterate through each one of these numbers, adding the next one in this list of numbers to the former. So one way that we could do this is we could say result equals, call the addition function. So addition num1, num2. And then we could say new result equals addition, and now we need to add the former result, and what we're adding is num3, and then we have a new result, which again we can call the addition and say new result, comma num4. Now if we hit play on that, we do need to print new result. Just copy and paste. And then hit play. So when we hit play, we can see the output, which has taken num1, added num2, taken that result, added num3, taken that result, and added num4. That's maybe slightly more condensed than if we were to just write out this line. In this case, the function is only performing one line of code, so it's maybe exactly the same as if we were to just write that out. And another way that we might do this is to just write out result equals num1 plus num2 plus num3 plus num4, and we could get that same exact result. A different way than writing out each one of these functions separately is using the kind of power of iterating with loops combined with the call of a function, or the kind of blocking out of a function, to iterate through whatever that operation is. So we can start by saying for I in range. And now if we're trying to figure out what the range here would be, let's say we have 10. So let's start with 10. This value is going to be wrong, but let's look at this first and see why it's wrong. So for I in range 10, we want to make a list of all of these numbers and say, for the first one, I want to add the first one and the second one. For the second one, I want to add the second one and the third one. Not add to the first operation, but just add just those two numbers. Then for the third one, I want to add the third and the fourth one. We can do this by iterating through each one of those items in the list. So we can use the item index, which in this case for I in range is going to just loop through a series of numbers from 0 to 9. So we can again remind ourselves by printing I here and hitting play, and we see it looping through those values of 0 to 9. So if we want a list of these number values, then we can say nums or numbers equals an empty list, and inside of this list we want to put num1, comma num2, comma num3, comma num4. So we now have 4 items that we're storing inside of this list. And just a reminder, indexes start at 0, just like this range. So we're going to go from 0, 1, 2, to 3. So we only have 3 index values in this list. So instead of printing I here, if we wanted to print numbers, open up that list, so open the box and then tell it what index we want to use. So print numbers of, we can use that I value to call some index in this list. So we can say for I in range 10, print numbers of I. So when we have an I value of 0, we're going to get a printout of num1. When we have an I value of 1, we're going to get a printout of num2, and then num3, and then num4. So I'm going to hit play here. And what happens is we get an error. Now we get an error because it says index out of range 4. That's because we only have indices from 0 to 3. So in order to coordinate those, we need to change this range value to match the length of our list. Now I can hit play, and we see that that works just fine. Alternatively, instead of having to count however many items we have in our list, we can just use a function inside of this range input, and we can say, let's use the exact length of our list, right? So for I in range, the length of numbers, meaning we'll never have an issue with an index that's out of range because we're using the specific number of indexes and iterating through those. So let's go ahead and just print I first, and I'm going to comment out that numbers, and we get 0, 1, 2, 3, which is exactly what we might expect and what we need to get indexes out of this list. So if I hit play now, we can see that it's now printing not 0, 1, 2, 3, which are the index values or that I value, but it's actually printing the item itself. So it's printing the value stored in num1, num2, num3, and num4. So to use this information in coordination with the function we've defined above, we need to call the function inside of our loop. So I'm calling this function addition inside of our loop here. And then we need to pass in some information. If I just pass in num1, first off, it needs 2 input variables, so we're going to get an error anyway. But it also would always be passing in the same information and not actually doing anything with it. Instead, we want to coordinate this with the looping that we're doing by using numbers of I. And then if we want to step through that list, first adding num1 and num2, then adding num2 and num3, and then adding num3 and then num4, we need to find a different way to call indexes in this list. So if I just had numbers of I again, that would give us a value of 0 and 0, and then 1 and 1, and then 2 and 2, and 3 and 3. So we would be adding the same number to itself every single time. I'm going to comment out that function call, and then again, we're going to just add a print I. So if we print just I, we know that that I value is going to be 0, 1, 2, 3 as it steps through each of the items in the range. If we want the next index to be added to the current one, we would want I plus 1, right? So if we're currently at 0 and we want it to be added to index 1, then we want 0 plus 1. Right? And if we're at 1, and then we want index 2, we need to add 1 again. If we're at 2 and we want 3, we need to add 1 again. So if we go ahead and hit play, we can see that we're printing, let me actually add these on the same line as well. So we get 0, 1, 1, 2, 2, 3, and 3, 4. So with this addition call here below, we don't want I for that second input. We actually want numbers of I plus 1. And if I hit play, again, we're getting an error. Now this time we're getting an error because if you remember from that printout of I plus 1, there's no such thing as the index 4 in this list of 4 numbers, and that's because the maximum index is 3. So what we need as a maximum here is the length of the list minus 1, because we want num1 to be added to num2, num2 to be added to num3, and then num3 to be added to num4. So that's only 3 times calling that addition. We don't need all 4 of those indexes, so we're going to say length of numbers minus 1. Now if we click play, it's going to perform that. We're not getting any errors. In order to read that out, we can just write a print statement on the function, hit play again, and now we have num1, so 12, plus 4.7 gives us the first value of 16.7. And then separate to that, we have 4.7 plus 7.1, which gives us a value of 11.8. And then we have 7.1 plus 11.2 gives us 18.3. So now this is significantly less code, essentially just 2 lines of code here, 3 including structuring the list, versus the, maybe 3 times as much that we would have to write out in order to perform the mathematical operation that we want here, right? Because we would have to say, we'd have to go one by one through and say result 1 equals num1 plus num2, result 2 equals num2 plus num3, result 3 equals num3 plus num4, right? So we have 3 lines versus our 2 lines here. And now if you include the definition for the function, we have a little bit more. But what if we want to do, instead of just these 3 iterations, we actually want to continue adding to this list, and we just want to say num1, num2, num3, and then we can just continue this again. So we'll just make it repeat num1, num2, num3, and then we can make it a little bit asymmetrical or non-repetitious here. So I'm going to just copy num3, num4, num1, num2, num3. So we now have a much longer list. Let's see if this code still works. I'm going to hit play, and let's see if we get an issue. So now what would have taken something like 12 plus lines of code to perform that exact same operation of going through this entire list takes 2 plus, really this is just 3, right? So we just have a definition line. This is the only one we need to keep, and then the result as well. So in 5 lines of code, we've done what would have taken us 12 plus lines of code. And as the kind of problem that's being solved becomes more complex, this kind of difference in efficiency is only expanded exponentially so. Another way of using loops in coordination with functions is going to be using a while loop. So we took a look at a while loop and basically understood it in the last video as something that would run until a condition is met. And I mentioned that these are dangerous because they could go on forever, so we always need to ensure that there is some condition that is being met. So if we wanted to use a while loop here, what we might say is, can you add all of the numbers in this list, so perform the addition operation on all of the numbers in this list to each other, adding them all up until whatever that variable is, so the resulting variable, is greater than some value, or run it until it's greater than that value or equal to that value. So if we wanted to do that, what we would need is to say result equals, and we can start with our result variable just equal to 0, because we're going to step through adding all of the numbers in this list. So while result is less than, and we can just try a small value here to start. So while result is less than, the first number is 12, so let's just go ahead and say while result is less than 14. Then do something until it gets larger than 14. So what we want to do is we want to say result equals, and then our call to the addition function, and we want to pass in these values, num1, num2, num3. If we just wanted to start off by using in the addition function the result itself, and then just one of these values, so I'm going to just say num1 here, and just to clarify what we're looking at, I'm going to clean this up with some print statements. So we'll print result, and then we will print as well num1. Okay, so we're going to print both of those values before we perform the addition, and then I'm also going to print result equals result after, we'll call it, equals result. So we have one result value that is before the addition is performed, and then one that is after. Now, if we take a look at this, if this addition function is adding and we have only positive values there, then we can ensure that this is always going up. Now, another way, if we didn't know that num1 was always positive, we might start actually adding a negative value, which could be really dangerous because then it could never meet the condition of being greater than or equal to 14. So to ensure that this variable we're passing in is always a positive, we can use an absolute value function. So ABS, which stands for absolute value. And that ensures that no matter what the value is, it's always positive. So we're always passing in two positive values, adding them together and getting a result, meaning we should never have anything but positive values, and it should quickly add up to more than 14 and stop the while loop. So if I hit play on this, we see it print first. So it runs the while loop, it steps into line 58, it prints result equals 0, num1 equals 12. It then goes down to result after, prints 12, because we've actually added together using our function 12 plus 0, which equals 12. We've overwritten the result variable, so it's no longer 0. Instead, result now equals 12 because we're setting it equal to that returned result from our function. So now equals 12. And then since 12 is not, it is still, right? So while this statement is true, so result is still less than 14. So that statement is true. So it is running again. So it runs again. It goes to this print statement again. And now it says result equals 12, num1 equals 12. It then passes those two values into our addition function, getting a result of 24. Now what happens if I make this 140? Well, now what's going to happen is it's going to iterate through adding in steps of 12, because our num1 value is 12, adding in steps of 12 until the result is greater than or equal to 140. So if I hit play, we're now getting that output, and we're seeing that result after is 48, 60, 72, incrementing in steps of 12 all the way up to 144. Now it goes all the way to 144 because it's still running that function in the last step when it was 132, which is less than 140. So it's going to run that function one more time, and then running that function one more time adds 12 and then gives you a value of 144 as the final resultant. Now, instead of adding just one value, what we could do is increment through the indexes of the list above and continuously add all of these values to our result, so just add them all up together to each other until we meet a certain value. So it's going to look very similar to this, but what I'm going to go ahead and do is copy and then comment those lines out and paste just below. Okay, so our result is still going to start at 0, so we can leave that. Our while condition is still going to be the same. We can leave that for now. Our print statement here we no longer need, and we'll leave the one at the end just so that we have some way of referring to it. We're going to pass in as one of the additions our result, but instead of the absolute value of num1, we want the absolute value of our numbers list at a certain index. So we want to pass in an index value here. Let's go ahead and call this index, because with a while loop, unlike a for I in range loop, also known as a for loop, we don't actually have an I value. So if we're trying to set or get an I value to be able to step through indexes, we need to find some way that we can develop an I value here that we can feed in as an index. Well, we know that we step every time and then we can perform an action here. So if we know that we want to start with an index value of 0 and we want to start there by feeding in our 0 index to numbers, that should at least give us 1, right? So if I hit play on this, which I'm not going to do just yet, all we would do is until that addition goes up to 140, we would be adding num1 again. So that's what we just did in the lines above. Right? That would be the exact same as this because we're never changing that index value. Instead, if we want to change that index value, what we can do is we can say every time we step, we should add 1 to the index. So the index equals whatever it was previously plus 1. If we didn't add itself in here and we just said index equals 1, then it would just go from 0 to 1. And then we'd be stuck at 1 again. So we need to say whatever it is, add 1 to itself. So index plus 1. The shorthand way of saying this is actually just index plus equals 1. Then I'm going to comment the rest of that line out. So we can shorten this to just index plus equals 1, and that's just a shorthand way of saying index equals index plus 1. If we print index, we should get that index stepping through, and I'm going to comment that other print statement out, and I'm actually going to comment, I almost did something bad, which is that I was going to comment out this resulting statement. So instead of using while here, what we're going to do is switch this, and we're going to say while index is less than 10, and comment out that result. We're adding 1 to the index, and now I'm saying print index index. So until index is greater than or equal to 10, we're starting at 0, so that's less than 10, so it would iterate. It would add 1. 1 is less than 10, it would iterate again. Then we'll continue printing index until it's equal to or greater than 10. So if I hit play, we see index 1, 2, 3, 4. And if I put this print statement above our addition, then we'll have it printing the value it was when it got passed through the while loop. So if I hit play, now we get 0 through 9. So very similar to a for I in range or a for loop, we can structure these while loops using an index by just iterating through in this way. So that way we don't need a condition there. Instead, we can just loop through with a given length of a list and then perform all of the iterations in the length of that list. We can now shorten these indexes like we do for I in range. The for I in range could also be a for index in range. So I'm going to just shorten that to I equals while I is less than 10, and I'm going to shorten that to I as well. And we can keep that print statement as I, and if I hit play, Good thing we got an error. We need to make sure that we're changing all of those variable names. So I plus equals 1. Now if I hit play, we have index 0 through 9 still. So now if we want to perform this addition using some index value, we can pass in that I value and it will iterate through 0 to 9 for these numbers. And if I hit play with the print unhidden, hit play, we get result equals 12 all the way through to result equals 88.3. But it's only iterating those 10 times, so it's not going all the way through this list. If we want it to go all the way through that list, just like with the for loop, we can just say for I in length, and then we can say here for I in length of the list numbers. Or rather, not for I in length, but while I is less than the length numbers. You can also check that length by printing the length above. So the length there is 13, so we now get 13 iterations, or 13 steps inside of this while loop as it iterates through all of the numbers in that list, adding them all to each other. So if I just cut this, move it down here, we now have a really condensed way of performing a pretty huge number for, relatively speaking, number of mathematical operations. So in just a few lines of code, we can perform this iteration through this entire list. In the case for this while loop, though, we're iterating through until this condition is no longer met outside of the function. So this is one way of doing this, or performing these operations with this kind of efficiency of pairing any type of loop with a kind of function, or the properties or benefits of a function. So we can really condense and get efficiency in our programming. But there's a slightly different way of going about this, which is going to perform, in this case, a pretty similar action, but really gives us the kind of true power of something like Python relative to let's say Grasshopper, which is a feed-forward based program, meaning that all of the nodes in Grasshopper just feed into other nodes forward. But what if you wanted to take the output of a certain function and use that as the input to itself? This is something that you actually can't do in Grasshopper, because it would need to first say, under this condition, I'm a starting value. It would perform the action, take that action, and give it into itself. There are plugins that allow you to do that in Grasshopper. One of them is HoopSnake, which allows for what's called recursion inside of Grasshopper. But in Python, it's actually really easy to perform this action by taking some value, performing an operation, and then inside of that same function saying, do it again, and do it again, and doing it again. And the way that you structure that is by not looping through here and calling a function inside of a loop, but just calling the function one time. Now, if you think about how you could possibly do this, so how can we possibly loop through something multiple times by only calling the function one time outside of itself? So I'm going to go ahead and comment these out, and I'll copy this addition function. Actually, we'll copy it down and comment that out as well, because I'm going to use that same name. Maybe I might change it, we'll have to see. And even though it's not at the top of my script, that's okay. We're still going to put it at the top relative to what we're working on. So we have that addition function there written out. So how could we call this function one time? So addition, feeding in, we'll say, we'll start actually with just one value. So we'll say num1. So passing in num1. And we'll just call this num as well. Okay, and I'm going to remove some of these. So perform an addition on a number multiple times without looping. So we don't want to loop. And we still want to use kind of some return, but I'll actually give a hint and say we're not going to use a return like that. So if we're not returning any information, then there's no way of reading this information outside of the function like we did with this while loop. We were using a return function to get that result value, override it, and then send that back into the function. So that's the way that we can work with functions and loops. But if we're not going to structure it that way, how would we be able to build up this function recursively or self-referentially to call it multiple times? Let's start by adding a variable here, num, and we can set num equal to 0. And let's pass in num to our addition function. And then inside of here, we want to say new num equals underscore num, which is the underscore num variable passed into our function, right? So we're changing that name just to keep things kind of proper and separate. So new num equals underscore num plus 1. So this is kind of like where we were iterating through and adding to our I value. So num is going to increment by 1. If we say here print new num, hit play, this is going to print a value of 1. It's because we've only called the function one time. So the num was 0, we passed that data in, it's now performed that operation, and it gives us a value of 1. If we're not using a return here, and we can't use a loop to iterate through or add multiple calls here, what can we do inside of this function to make it run again? Well, we could say addition num again and hit play, but that just prints the same value twice. So it's just performing that same exact operation 2 different times. What if instead we add the function call inside of the definition for the function? What happens is first Python ignores this definition. It goes down to our num variable, which we see it num equal to 0. So we're declaring num equal to 0, storing that in the name num. We're now calling the function addition. So it's now looking back up here and seeing that there's a definition for that function. We're feeding in that num value, and now if we open up that definition, we can see we're performing an operation which is adding 1 to that variable, or a new variable now that we're declaring here. We're printing it, we're calling the function again, which would go back up to line 76. We're passing in num here, so actually that should give us an error or some issue because we're passing in a value that's actually non-existent inside of this function. So first thing we would have to do in order for this to even work is to hit underscore num. And really, if we want to take advantage of the operation we're performing, we would want to use that new value, new num. So we're performing that operation, taking the new value, passing it into the function again, which comes up here. We read that not as new num, but now as underscore num, perform the operation by adding 1 again, get a new value, and it would go on in this loop forever. So we don't want to click play right now, because it would go on forever and crash our computers. So instead, we want to ensure that there is some condition that this will no longer run. What we can do is say run until, so only call if new num is less than 10. Let's tab that in and take a look at what we've just written. So new num equals underscore num plus 1. So we're getting that in here first, and it's 0. 0 is being passed in, so if I just replace that. So we have 0 being passed in. 0 comes down here and replaces this underscore num, so we have 0 plus 1. Okay, well, that equals 1, so we're passing in 1. This would print 1. If new num, so if 1 is less than 10, 1 is less than 10, call the function again. Okay, 1 goes in here then, because new num equaled 1. So now we're calling the function, passing in 1. Now we have 1 plus 1 equals 2, so print 2. 2 is less than 10, pass in 2. 2 comes up here, and I'm not going to go through this all the way through 10, but hopefully you get the idea that we basically structure this in a way where we have a value being read in, operated on, a new value or variable being made, so new num, and then here, if we just left that, if 2 is less than 10, we need to be really careful about that because 2 is less than 10 forever, and we're not performing an operation on the integer 2. We're performing an operation on the variable new num. So if we set it like that, if new num is less than 10, as it continues to step, we're going to eventually see new num being 10, and then it will no longer call this function. So if I hit play here, we get it printing out. So it's printing out 1 all the way to 10. And that's because eventually it's 10. 10 is not less than 10, so it doesn't call it anymore. You can even write this print statement inside of this conditional, and we'll no longer see that last 10. So if I hit play, we get it running from 1 all the way to 9. So this is the exact same kind of operation, but we just nested that print statement inside, and we can see that it stopped at a value of 9. It no longer ran that conditional or called this function once it got beyond a value of 9, which is 10. So although this is slightly interesting as a kind of premise or principle with just abstract numbers, and it's a really condensed way of writing what we just did, right? So it's a way that we could kind of replace this whole list of numbers by iterating through calling itself and referring to the thing itself. That's an interesting kind of abstract condition in and of itself. Where it really becomes useful is when we pair it with something like Rhino geometry, being able to perform an operation on an object and then take the output of that operation as the new input and then continue that process. So imagine if we had a point and then we said, let's move this point here. Okay, now I want to take that point and move that here. Or imagine we said, okay, we have this point. I want to copy it to the left, and I want to copy it to the right. Okay, well now we've created 2 objects. What if at each one of those points, they each become an input into our recursive function? Right, so we call that same function, not just with one point, but with each of these. Well, then what we would have is 2 more points being made from both of those. Okay, now it's not just these 2, but it's all 4 of these that are created. So all 4 of these points are the new base points. So now all 4 points get a set of 2 points. And then it continues on and on and on. And so basically this is the way that we're going to be able to perform fractal-like operations, exponentially increasing the kind of processing power, action, or operation that we're trying to perform. You can see how quickly that builds up just in using points, going from 1 to 2 to 4, and then to 8, and so on. And this is what's going to be called recursive aggregation or branching. And this is one of the primary uses for this. So in order to get started on this recursive aggregation, I'm going to save this Python file, and then we're going to open up a new empty Python file as well. And then I'm also going to minimize this Python script for a moment. And what we're going to do is build an object actually that we can use for our aggregation. So what we're going to use is a tetrahedron. I mentioned in the prior video that a tetrahedron is a really nice kind of unit or object for aggregation because all of the faces are exactly the same, meaning it can aggregate on any side, it does not matter. Or another word for aggregate is it can orient on itself no matter what side it is, because all the sides are totally equal. All of the edges are. So just a reminder, to make a tetrahedron, we need a point at the origin and then a point 10 units away. So we have these 2 points in space. We can then draw a circle centered on one and a circle centered on the other. And where those 2 radii intersect, we can drop a point. And this point we know will be equidistant. We need to make sure that our center snap is not on and that our intersection snap is on. Another way that we could do that is just select both of these and type intersect, which would give us those points. Now, if I delete those circles, we have 3 points here. And now we just need the 4th point up in space, which is 10 units from each of these. So to do this, we need to draw a sphere from one point to the next, from this last point to that same point. We can turn shaded view on, or maybe ghosted view so that we can see the points as well. Select both spheres, type intersect. That gives us a vertical circle. And now if we draw a sphere centered on this point to one of the other points, that's going to make a sphere of radius 10. So wherever that intersects with this circle is going to be exactly at 10 units from that point. And since this circle is the intersection of the other 2 points, which had spheres of radius 10, we know that that happens exactly at 10 units away from each of these points. And we have a bottom point there, which we don't need. And we don't need this to be at the origin, so just so that we can see it a little bit better, I'm going to move that off. And now we just need to draw each of our surfaces going counterclockwise 4 points. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then last one we need is just this bottom surface. 2, 3, 4. Okay, all of the sides selected. We can now join them and hit enter. So the basic idea here, we went through this in one of the previous videos in the introduction to Rhino, but we're going to use the command orient 3 point. First, place 3 points as reference points counterclockwise, so 1, 2, 3, counterclockwise. And now if we want to orient this object onto itself, what we need to do is just to reverse the order of those points by now going clockwise. So just 3, 2, 1. So we've now oriented that onto itself. So already this is the kind of language of what those recursive functions were doing by calling themselves, and then wherever it is now is the new object, right? So now this is the new object. And again, we can draw counterclockwise and then clockwise. And we have a new object. Now we can use it again itself. So it kind of uses the same language naturally. In that example, I didn't have copy on, so we weren't actually building multiple objects, we were just moving it in space. So with this whole process, we can do that as well and just see what it's like just moving it in space. But we're also going to be able to actually copy it and grow objects in space. So we'll do both so that we can see what the differences are there. But the first thing that's important before we even get into the coding is to really understand the logic of this, or the logic behind this. So when we're using this, we have the object itself. What actions we're performing inside our head that we're maybe not kind of consciously thinking of is we're selecting one particular face in this tetrahedron. So I'm saying I'm going to choose this face to aggregate on, right? So I'm selecting that face, and then we're selecting the points on that face, clicking through each one of those points, and then reversing that list of points to send into the orient command to orient the whole object. So what's involved there is the selection of the face itself, this face versus this face versus this face. Which one do we want to use to aggregate? Which set of points do we want to use, which are the corners of this face? And then taking those lists of points, taking one just counterclockwise and one clockwise, or reversing that list, feeding it into an orient command, and then performing that orient. So that's everything that's involved. To look a little bit closer here, I'm going to just add labels to our object. So I'm going to add text dots, and we're going to call this by index names. So I'm going to say this is face 0, face 1. Also, we can move these. I'll move it up in a moment. So, and then face 2, so that it's not confusing with the base. So I'm going to just move these up, scale them in slightly so that they're closer to those faces. And then the fourth index is just going to be that base, which is index 3, which is the fourth index. And that happens on that bottom surface. So those are the indexes of all of our faces. We have 4 faces in this tetrahedron, ranging from 0, 1, 2, and 3. Now on each face, we have a different set of indexes for 0.0, 0.1, and 0.2. But then we also have a value for 0.3, which is this 0.0 itself. So I'll just put it very close there. And then I'll select all of this and just group it together. So now when I perform this orient 3 point, and if I say copy yes, when I click on this top point, and then make 3 reference points around here, we go from 0, 1, 2, 2, 1, 0. And if we take a look at that on every single face, what we're doing is we're calling out certain indexes on each face. So even if I want to change it to a different face and not use that same one, I would now do that same thing and go counterclockwise. 0, 1, 2. Actually, sorry, we were already snapped on there, so I'll just finish it out here so that's clockwise. And now again, clockwise here. So we're going to go from this point index here. So we now have that object aggregating or iterating in space, just from that orient command. So when we go into Python, we're going to first need to read this tetrahedral object. We could also just write it directly inside of Python, but it's going to be easiest if we just go ahead and first copy, ungroup, just select these surfaces, and move those over here, and then join them back together again. So, okay, we have that closed solid poly surface, and we can go back to shaded view. And I will type isolate. Okay, so we have that object there. So it's going to be easiest if we just read that into Python, which is going to look kind of similar to the way that we reference geometry from Rhino in Grasshopper. So it's not the exact same method, obviously, they're very different, Python and Grasshopper, but it's going to have a similar logic where we have an object in our Rhino document, and we need some way of referring to it in our Python script. So if we go back to that Python script, and I'll just say here, recursive tetrahedral aggregation. Okay, the first thing that we need to do, as we do any time that we're using Rhino geometry, is import Rhino script syntax as rs. Now that we've done that, we have access to our Rhino functions. We have our tetrahedron drawn out inside of Rhino. We need some way of getting this into our Python script. Let's go ahead and take a look at our Rhino script syntax tab on the left, and let's see if we have some set that would be helpful for this. So we have a geometry tab here. In our geometry tab, we have add point, which we've used a lot. We have, what else? Point clouds, point coordinates, not quite. Let's see what else we have. We have object. So in object, we have copy object, move object. This is going to be very similar to the methods that we've used inside of Rhino for moving and copying. We have object color, so we can add a color to the object. We have object name, rotate object. We have orient object, which is going to be something we need to refer to later on in this script. So let's remind ourselves that that exists in the object tab here. So orient object. We even will see that there's an example here, so we can refer to that example. And this example is actually giving us a hint of what we need. So it might be best to just go directly to that orient object, and we can take a look at the structure here, because we're going to be building a pretty similar structure for ourselves. But the main thing that we're seeing here is that we start by selecting an object using a getObject function. So getObject we need to find in our list here to the left. So under the selection menu, we can see that we have our getObject function. And when we take a look at this, it's going to take parameters message, so a prompt or message, an input of a string, which is optional, it says. So prompts user to pick or select a single object. Then we also have parameters of filter, so a number optional, the types of geometry that can be selected. So if we wanted to specify only to select surfaces or only to select meshes, we could use a number value or a name. Points, curves, surfaces, meshes, which are 0, 1, 2, and 3 indexes. So you input the number of those values. You could also pre-select, so allow for pre-selection of the object. Select the picked objects, so if false, the objects that are picked are not selected. And then we have an option for sub-objects as well. So the main thing we want to focus on is just going to be this message input. I'm going to open this function by typing rs dot, and then we'll type the name, so getObject, open parentheses, and we can see some differently structured information, but the same basic information we were just looking at. So it takes an input message, which by default equals none. We could just close the parentheses there, and if we hit play, then it will still say select object, and then we can left click, and it looks like nothing's happened, but what we've done is just selected our object and somehow brought it into this Python script. Now, if I hit open parentheses again, what we want to do when we're looking at these is take a look at what the function returns. Does it create a geometry? Does it add something to the document? What does it actually do, and how can we interface with it? So we know that we have an option to input a message to ourselves to prompt us to select something, but then we also have here what it returns. So it returns from the function, just like we did in our functions, right? So it returns by using the return portion of the function to output information to us. What does it return? It returns a GUID so that we can call that object in our document. So it gives us the kind of variable name, GUID name, for that object in our document. So if we want to give ourselves a message, which I recommend that we do, we want to give ourselves some information or indication of what it is to select. Otherwise, it just says select an object, and you have no idea what you're selecting. So we're going to say, please pick we could say a tetrahedron, or we might come back to change this to make it even more versatile so that you could put anything you want in here and select any geometry type, and it will still perform the same function. And that's the point of functions, is the versatility. So please pick a tetrahedron, and we could say tetrahedron object, or polysurface, if we wanted to specify that that's a polysurface and not a mesh. So please pick a tetrahedron polysurface. Now, if we wanted to, we could also specify with a filter to only allow selections of polysurfaces. So we could do that. We don't necessarily need that. If we wanted to do that, we need an rs.filter, and then we use rs.filter dot, and then whatever type of object that we want to filter. So we're going to say filter polysurface. So that only allows for the selection of polysurfaces, and then it says please pick a tetrahedron polysurface. Now we can just get rid of the polysurface because we're already filtering only polysurfaces. And now here we have GUIDs, so we can say tetra or polysurf. Maybe let's call it polysurf just so that it's a little bit more generic. And now when we click play, we get a note that says please pick a tetrahedron. I can left click on that object, it finishes the command, and then our Python script loads back up. We want the information from this polysurface or this function we're running. When we hit play, we can pick the tetrahedron, and it now prints out that GUID. So this is the first step, is to get our Rhino object. Once we've gotten that object into our Python script, we need to prep a few things like we did in Rhino, right, by constructing those point indexes and kind of understanding the geometry. So we said that in order to orient, we need 3 reference points, and we need to select a face to orient on. So what that means is we need to change this polysurface from a joined polysurface to each of its surfaces. So let's type in rs and see what we have here. If I scroll through here, it might take me a while to get through. But let's see if there's something under explode. So we do have something called explode polysurfaces. If I double click on that and then open parentheses, we see that this explode polysurfaces takes in object IDs. Well, that's great because we just got an object ID, a GUID, and we just saved it as a variable polysurface. So let's try plugging that in, polysurface, and then delete input equals false. Yeah, it's fine. We don't need to delete that, so we can leave that false. And then the output is a list of GUIDs of identifiers of exploded pieces on success. Okay, and then if we see the example, we can see that it says obj, which is the result from get object, and then if is polysurface, which we don't need because we're filtering polysurface. But I suppose if it's a none value, because we didn't select anything, then that could cause an issue. So we can use that conditional if we want, just to be safe. But then we say rs.explode polysurfaces obj. Okay, so that's what we have as well. And then let's go ahead and just print this to see what results. So print rs.explode polysurfaces, pick a tetrahedron, and now we have a number of GUIDs printing out here. And we should see 1, 2, 3, 4, and that's it, which is great. That matches the number of faces that we have. So 4 faces from our exploded polysurface. That's fantastic. So let's go ahead and call this surfs, which is a list, and we're just directly going to take that list of GUIDs and save it into surfs. Next, we want the corners of these surfaces. So in order to get the corners, we need to make that selection of which surface we're referring to. So one way we can do that is looping through each of the surfaces, saying for, and what I'm going to say is for item in surfs, just directly iterating through the items in that list. And instead of just generically referring to it as item, we could also just save a variable called surf. So for surf in surfs. And just a reminder, this is the exact same thing as saying for I in range length surfs, and then saying surf equals surfs of I, right? So we still get the variable surf, it's equal to surfs of I, and we're still looping through that list. But it's just much, much quicker to directly say for surf in surfs. And now we can just loop directly through that list. So for surf in surfs, corner points equals, and then we need to try and find a function that takes the surface, oops, not surface area, surface, let's see what we have under surface. So we have surface area cone, surface points. Let's open up this and see what this does. So, okay, under surface points, we have an input that is required of a surface ID. Well, that's what we have, and it's now currently stored in this surf variable, srf. It returns a list of points, the control points if successful. Okay, so let's input here the surf that we have that we're looping through, save that into our variable or list actually for corner points, and then let's print those corner points. Hit play. It's going to ask us to pick our tetrahedron. I'm going to pick the poly surface. We've exploded this a few times, so we actually have these surfaces that are the exploded polysurface faces. But when we hit play there, we can see that we have, I'll expand this so it's a bit easier to see. We have 4 lists and 4 separate lines. And that's because we're looping through each face in all of the faces, so in the list of faces. And inside of each face, we have 1, 2, 3, 4 points. 4 corner points. Just like when we clicked to make that surface, we clicked 4 times. So those are the 4 points. And then we have those points located at 23.21, 35.75, and 0. And then we have 23.21, 35.75, and 0. And then we have 28.21, 27, and 0. And then we have 18.2, 27.0, and 0. So all of those values are different except for the first 2 points, which are exactly the same. Now that's because our 0th and then our 4th point, which in this case it's actually index 0 and 1, are the same because the surface connected back to itself, right? So we closed it out so that it is an untrimmed surface by adding 4 corner points. And now let's go ahead and check these ones as well. So those are also the top point. So that top point again is a consistent point for each one of these surface corners. and they have 2 of those points in each of the surfaces. So we just want to be careful that we're not selecting those point values that are the same, which are the index 0 and 1 for each one of these faces. So we don't want to be using index 0, 0, 1, and something, because that would just give us essentially 2 points, which doesn't actually construct a plane. So we need to be using either index 0 or 1, and then 2 other points, so index 2 and 3, in order to construct the 3 reference points for our orient. Okay, so use index, let's just say use index 1, comma 2, comma 3 for orient 3 point. Now we can remove that print statement, and then under this comment, we can now start to structure this. Orient command, or this orient operation. So we have the corner points, we have the surfaces. What we want to orient is actually going to be our polysurface. So we don't want to orient all of the individual surfaces. We want to orient the polysurface itself. And as we saw earlier when we were taking a look, we saw that orient is a command here. So we can just type in rs dot orient object, open parentheses, and we can see this takes in an object ID. Well, we want that to be our polysurface, so I'm going to feed in our polysurface, and then a reference and a target. And then if we look a little bit closer in, we see that it takes either 2 3D points, which is orient 2 point, or if we give it 3 3D points, then it will read it as orient 3 point. We then also have options for copy object, so the default is to not copy the object, and that just comes in under these flags. So what we need here is a reference and a target, and then to set these flags, where 0 is no copy, no scale, but we actually want to copy our object as it's orienting. So I'm going to change this to 1 to copy that object. Okay, now our reference and target currently are undefined, so we know we need to construct those, we need to declare those variables, and we need to set them equal to something. So we already said here, use index 1, 2, 3 for orient 3 point, so we can say reference equals, well, reference equals corner points, we've already written this out for ourselves, corner points of, and then we have index 1, and this needs to be a list of points. So we can't just say corner points 1, 2, 3. Instead, we have to say place this inside of a list, and we're going to use the first item in that list as corner points 1, and then the second as corner points 2, and then corner points 3. So now we have a list of 3 points, 1, 2, and 3. Now we've already said this, but our target is just going to be the flipped or reverse version of reference. So we can copy this list down here, and then just change these indexes to 3, 2, 1. So we're just reversing those, just like we did inside of Rhino. Now we have those references and targets set, and if I hit play, and then select the tetrahedron, we get a new tetrahedron drawn out at every single one of those faces. We also are getting each of the surfaces from that explode. What we could do is, after iterating through, we could take that list of surfaces and we could use a function, so rs dot, to delete the objects in the file. So we don't want delete object because that's just singular. We actually want to delete a list of objects, which would be delete objects. And if we open the parentheses here, we can see what this takes. So a list of object IDs. So we can just feed in surfaces, put that at the end of our script there. And now when we run it and click on this tetrahedron, it's going to loop through, explode the surfaces, loop through the surfaces, aggregate or orient them onto one another, and then it's going to delete the exploded surfaces. So we don't have to clean that up anymore, which is great. So when I click play there, we now just have 5 poly surfaces, including the original one, and then from this loop, we have a new one on each point. Now, what if I wanted to do this not just for this set of tetrahedrons, but I also wanted to do it for all of these ones I just created? Well, first, we wouldn't want getObject. So I'm going to copy this down and then comment these lines out using Control /. We need get our Rhino objects. Plural. So we can't use getObject here. We need a function which is just getObjects. So this is going to allow us to pick multiple objects. Pick all tetrahedrons. So we're going to now pick multiple objects in our file. Right now, though, we're reading this as one polysurface. What we want to do is loop through each one of the polysurfaces that we're getting. So we know that we want that all nested inside of something. We have multiple polysurfaces in this list as an output of getObjects. So what we need to do is say for, just like we're doing for the surfaces, for polysurf in polysurfs, and then loop through this. It's just as easy as that. You just need one extra line of code to adjust one letter in 2 letters in line 26 there. So if I now click play, it's saying pick all tetrahedrons. I can select all of these tetrahedrons, hit enter, and now for each one of those, it makes another set of 4. So we now have 25 total, including the original 5. I guess we had a set of 5, so 5 times 4 plus 5, so 20 plus 5 is the 25. And now again I could hit play, select all of these and hit enter, and it's going to continue to iterate on every single one. And we see that they're not nesting perfectly well there, so I'm going to just hit undo, undo, and then undo until we're just down to our original tetrahedron. So instead of just continuing to iterate on more and more and more tetrahedrons, what we can do is actually create a function that allows us to not just take one and then continue to just orient on all faces, but takes one, selects a face, orients on that face, takes the new object, feeds it into the function, and then orients on that one. So what we want to do is translate this then into some function. So we can say, let's say this is back to, well, actually, we'll just go ahead and comment that out. And then we're going to copy our singular version, because we just want to use one singular polysurface, since it's going to quickly get complex as we build this function. And then inside of our function, we want all of these kind of different definitions, different operations on our tetrahedron. So I'm going to call this def aggregate. And inside of here, we want to perform all functions for tetrahedron aggregation. Okay. So if we already know that we want to do this, like we did as we were just looping through each polysurface we wanted to operate on, but every time we run this function, we can just go ahead and copy and paste this, make sure it's tabbed inside of this function. So first thing we're going to do is read in our poly surface, or tetrahedron, and then explode two faces. And now we don't want to loop through every face, but we just want to select one face to orient with or on. So that's going to be slightly different, so we don't need that loop there. And then we can tab this all back one using Shift Tab. So we need to get surf, and the way that we're going to do that is just surf equals srfs, so all surfaces, and then we just need to feed in an index. So we can start with just an index of 0. So we'll just start by iterating only, or aggregating only on our index 0 face. Corner points is still going to be set as that, and we can still use our reference and target as the exact same values. And then we still have orient and then delete objects. So that should all be fine as well. Okay. And now we just need to call this function, aggregate. We need to feed in our poly surface, so our geometry, polysurf. And then we need to read that in here, which, as I mentioned, our convention is that we don't use the same names inside and outside of the function. So we're going to use underscore polysurf inside of our function. Okay, and now if I hit play, I should be able to select this tetrahedron, and it will aggregate one time, orienting on one face, which is the bottom face. If I change this index value of our surfaces and then hit play again, it's now going to pick a different face to aggregate on, which is this one. I can undo that. I can change it again, hit play, and now it picks a different one. If we want to run this multiple times, we could loop through this function, or as we went through earlier in this video, we could just call this function from inside of the function itself. If we're doing that, what we need is to save this oriented object as a new polysurface object so that we can get that output and then feed that new output into our aggregate function again. So this is where the recursion starts to play out. But anytime we add a recursive call inside of the definition for a function, we need some condition to break it. And when we use recursive aggregation, typically what we do is we structure it around a number of generations. So we say, run this 4 times. So if generation is less than, or let's call it gen, is less than, and then we would have some value here, so we can say 4, then call aggregate. Now we need to define our gen here, and if we define it after our get object, gen we can say starts at 0. We then need a way of passing it into our function. So we can do that by passing it into our aggregate function. Now we need to set that up in our definition. So here we can say underscore gen. So we're now reading in that gen into our function. We now need to adjust this conditional to be underscore gen. Each time we run this function, we need to add to gen, so gen plus equals 1, so that each time we step, telling it that we've done one more generation. And now we can say if gen is less than 4, so each time it will add up by 1, so it should run 3 times. And then it will call itself again. And then lastly, we need to put our new gen value as an input to our aggregate function. One error that we have there is that actually our input to that rs.orient object function was just polysurf or PLY-SRF, and we were actually missing this underscore. So again, I can't stress how crucial it is that each one of these variables, especially when working with functions and the inputs to functions, are carefully labeled so that they don't read the global or external variable like PLY-SRF, which we're setting here, but instead it's reading the underscore PLY-SRF. So we're feeding in underscore. We have underscore here. So I've already made that adjustment. So now when we go ahead and hit play, it's going to go through this operation, running this function recursively. And we should see it run for 4 generations. So when I hit play, it's actually performed those 4 generations, but because our face index hasn't changed, we're selecting face 2, building an object or orienting an object and copying it to that position. It then copies on itself with that same exact face, and then it continues back and forth several times. So we have 3 objects there, including the original, and 2 objects here, the 2 that we've oriented. So if we want this to actually move in space, rather than just copying on itself, we can first visualize what's actually happening by changing this flag back to 0. And that's going to not copy the object, but we'll actually see it kind of dance around in space. So first, let's just do that to visualize what's happening. So I'm going to hit play, select our object, and we'll see it move around in our scene. So if I click play, we see it's just alternating back and forth. Then it ends where it began because we have an even number of generations there. So alternatively, we could use a different set of faces each time we wanted to perform this orient action. So think of a way that we might be able to iterate through this index input using something that we already have. So we know that we're iterating through or adding 1 to the number of generations here. So one way that we could do this is just take our generations and plug them in here. Now, when I click play and then click on our object, it's going to move through, moving this in space, first selecting index 0. Well, actually, we immediately add 1, so it's actually starting at index 1, so face 1, then face 2, and then face 3. But then it gets to face 4, which we actually don't have an index 4, because we only have 0, 1, 2, and 3, meaning 4 faces. So if I undo in Rhino here, we need a different way to maybe use this iteration information, or alternatively, in this example, we can just move this gen plus 1. So in this particular example, we just add this gen value somewhere else. Now what we can do to condense this a bit is we can run the test if it's less than 4. If we want it to stay 0 all the way through here, then we can just add that 1 value inside of this conditional. So only if it is less than 4, then add the 1 and run it again. This will still allow it to run for 4 iterations. If we wanted to condense this even further, getting additional efficiency out of this, we could just take this plus equals 1, and what we could do is just feed in here, not plus equals 1, but just gen plus 1. And if we delete this line 68, what we're now doing is not passing in the gen we're getting, we're passing in the gen plus 1. If gen is less than 4, we're adding 1 to gen, we're starting at 0, so when we pass these through, we're now using a first index of 0, then 1, then 2, then 3, which is still less than 4, then it goes to 4, so it still will be 4, which is not less than 4, so it won't run the aggregation again, but we're still going to get that same error. So if we select that, we see it moving in space, and we'll just run that again just to see it moving. So we still see it moving, but then we still get to that 4th index, and we have the issue there. So the way that we can prevent this is by using what's called a modulo. Now, there's several alternate ways of doing this and selecting the face, which we'll go through using conditionals in a moment. But the absolute simplest way to change the face that we're using based on the generation is to just use what's called a modulo, which is going to limit, or we can find a way to limit the output of that modulo, which basically says which step out of a certain number of steps it is. Now, really what a modulo is performing is a calculation to find the remainder. And we can take a look at this here in a moment. So if we want instead of feeding in gen here, we want a face index. So we're going to call that face index. Now we need to make a variable for face index, and we're going to set this equal to _gen. And to use a modulo, it's actually symbolized by a percentage sign. So _gen modulo, or percentage, and then however many steps we have, which what we could do is say length of surfaces minus 1. So that's going to give us our value of 3. Alternatively, we could just use length of surfaces, and let's just go ahead and print face index and see what this gives us at each step. So I'm going to hit play. We're going to select our tetrahedron. Surfaces, not surf. So we need to make sure that that's the length of the list, surfaces, so plural. And let me just undo that so we only have the 1 there. So hit play, select that, and we see our tetrahedron kind of dancing around in space. We're no longer getting an error message, and what is showing up in our console log? What's showing up is 0, 1, 2, 3, and then when we get to that 4th index, it goes back to 0. That is happening because actually what this statement, gen, modulo, and then some value, what this is saying is gen modulo 4, because our length of that list is 4, and it takes the specific current gen value. So when we start at 0, well, 0 divided by 4 gives you a remainder of 0. So 1 divided by 4 gives us a remainder of 1. 2 divided by 4 gives us a remainder of 2, with the quotient being 0. 3 gives us a remainder of 3, with the quotient being 0 as well. And then we get to 4, which gives us a remainder of 0, because 4 is divided by 4 one time, with 0 remainder. Now when we get to 5, we again have 5 divided by 4, so we can take out the 4. The quotient is then 1, because 4 goes into 4 one times, with a remainder of 1. And then 6 is 2, 7 is 3, 8 is back to 0, because 4 goes into 8 2 times, giving us a quotient of 2, a remainder of 0. So that's how the modulus is working inside of Python here. But it's really a way that we can just operate on a certain list or construct indexes by this process of kind of stepping. So it's a way here we can ensure that it ranges from 0 to 3 based on an infinite set of numbers. So it will never be anything besides 0, 1, 2, or 3. And we can ensure that because you can never have a remainder larger than 4 or equal to 4 if you're using 4 in a modulus. So if you're dividing by 4, you can never have a remainder larger or equal to 4. So I'm going to switch this back to length of surfaces because we don't want the value 4 necessarily. We want whatever our length of our surfaces are. So if we had, 20 faces, then we would want that value to be 20, and we'd want to have steps from 0 to 19 so that we can ensure our index values are correct. So if I delete this, we can take a look again at what's happening inside of Rhino. I'm going to undo, hit play, and then click. And we can see that we're moving that tetrahedron in space. Now, to see it actually aggregating, what's happening again, just to clarify, is that it's cycling through selection of face 0 first, then 1, then 2, then 3, then going back to face 0. And if we set this flag to copy, so flags equal 1, and then hit play, we'll see this actually aggregate once we've selected our object. So we get that aggregation in space. Now, if we increase the gen value here, hit play, select our tetrahedron, we see that same operation just continue one further step. Another way that we can think about this for the generation conditional, if we don't like capping it as less than some value and changing that value here, we could say run as long as generations is greater than 0, subtract 1 every time we run this, and then here where we have gen equals 0, we can just start with a certain value. So we could give it an input value of 10, and every time we feed in a value, we're going to subtract 1 from it and run it for as long as it is above 0. So it's a count down instead of a count up. This way, all we have to do is change this one number value outside of the function. Sometimes that's a little bit easier for us to be able to manage in a script, especially if we want to just keep that function hidden. Then all we have to do is just adjust this one value here. So if I hit play, select this tetrahedron, we can see it iterating or moving through space and creating this aggregated structure. So that's with 10. We could increase this even more, let's say 40, hit play, and now it's going to step through and aggregate 40 different times, so 40 steps, using the index value of 40, or whatever the generation is, but all the way up to 40, modulo the length of surfaces, which is 4. So it's iterating through 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, all the way through 40 times. So that gives us a relatively linear structure. Now, what if we wanted to, say, use the modulo for most cases, because we know that since it's cycling through, we actually get a pretty kind of linear or sprawled out or stretched aggregation pattern. And that's just because it's rotating every time, so it's not going to, use the same face and then a face next to it and just create a kind of circle pattern for that aggregation. So if we just said use face 0 here and then 1 and then 0 and then 1, there's a chance that depending on what those faces actually are on our tetrahedron, that it could create a kind of tight circular aggregation pattern, which would then self-intersect and all types of other things that might cause issues depending on what we're trying to use this for. So one way that we can control this pattern is by using conditionals. So I'm going to say control face selection using conditionals. So right now we have one condition, which is basically just saying all the time, use generation modulus length of surfaces, and that gives us that linear pattern. So let's say, let's say we want this to happen at all times, except for one particular condition, and that condition is going to be if underscore gen modulo 3. Yeah, let's start with 3. And what we want is not just if gen modulo 3, that would give us for 0 a value of 0, and then 1, 2, and then 0. So it's going to step through 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. So we need to give this a statement of equality saying if this is equal to something. So do we want it to equal 0? Do we want it to be equal to 1? Do we want it to be equal to 2? If we want this to happen not in the very first step when it equals 0, but we want it to happen in the third step, then we need to say if gen modulus 3 equals 2. Then we need a colon, and then we need something inside of here. So what we can do is we can say if this condition is met, then face index, so that face index equals, and then we could just pick any number from 0, 1, 2, or 3. So any number here, let's just say, and we'll say else, so under all other conditions, face index is still going to be equal to that exact same thing that we had. Now if we hit play, I'm going to zoom out slightly so we can see the full aggregation, and then hit play here. We see the pattern starting to tighten up, and that's because we're disrupting the pattern that we just had by placing in that index of 2 here. So index 2 every third step, so 0, 1, 2. And we can double check this by just printing out print gen modulo 3, undo this, hit play, select our tetrahedron, and then we'll take a look at those print statements. So in this example, there's a lot of self-intersection, but it goes 1, 0, 2, 1, 0, 2, 1, 0, 2, 1, 0, and so on. So right now at the third step, that remainder equals 2, which means that condition is going to be met at the third step, which it then changes face index to 2. So it goes 1, 2, 3. So this is step 1. And then it looks like step 2 is inside of there hidden. And then it goes to step 3 here, which must be that condition being met. It then looks like it might kind of come back on itself, so turn around, and then it continues with that pattern. So extending out, turning back around, extending out, turning back around, and that's why we see that kind of bunching pattern. We could change either the face index or the condition. So what I'm going to do to start is just go through a series of face indexes, trying from 0, 1, 2, and then to 3, and see how this affects the pattern of aggregation. So still the same condition, but just a different face index. And this should be something happening, some kind of change or shift in the pattern happening every third step. Something else that's important is that our modulus here is a different value than our modulus in the else statement. That way we can ensure that they are kind of off of one another. Now they might have overlaps where they're the same value, but since it's a value of 3 and 4, we're only going to get the overlaps in the multiples of these values. So I'm going to hit play, select our tetrahedron, and we can see this is a slightly different pattern with a much longer loop before that self-intersection occurs. So these are not perfectly space-filling tetrahedrons. In order to make them perfectly space-filling, we need to combine these regular tetrahedrons with a regular octahedron. And we can make a combined unit, as I discussed in the previous video on Rhino modeling, that actually does fill space evenly. If we undo this, I'm going to just try index 1, hit play, and we can see that pattern. Looks like there's a lot less self-intersection, and it's a more linear pattern, but still pretty tightly bundled there. And then we've already tried 2, so I'm going to just jump to 3, hit play. Now this seems to be a successfully non-self-intersecting pattern. So since this is a pattern that's continued across these steps, we can be pretty confident that if we increase that number from 40 to an even larger number, we should be able to actually see this continue on with no self-intersections. So if it doesn't self-intersect within the first X number of steps related to your conditionals here, then we can almost positively ensure that it won't have an issue or won't self-intersect at later stages. So I'm going to just double this, and we can go all the way to 80, hit play, and then select our tetrahedron, and we see that pattern continuing on, with still no self-intersections there. And we could just continue increasing that number value until we get the kind of density or length of that aggregation that we would like. Alternatively, what we could do is add another conditional statement. This time we don't want to say if again, because we already have an if statement, right? So if modulo 3 equals 2, face index equals 3. Okay, well, if we want to add another conditional inside of here, we need to use an elif statement. We can then say elif. Now here we could say elif gen equals, and we could just give it a number. So if it equals 17, throw off the pattern. So give it some other value. So we could say face index equals let's try 1. So just at one time, we are going to make the face index equal to 1. Now if I hit play, we might not even be able to notice this. It might be too subtle since it only shifts that one time. Let's see if we can try and figure out where it's happening. So I think I do see it happening. It's somewhere here where we've actually changed the kind of hinging of that aggregation pattern. So it's a little bit looser right around here. Looks slightly looser. Now I might just be imagining that, but I do think it's changing. I can't quite tell, but maybe this hinge between these two. So it's changing the face selection there. And I believe the hinge is getting a little bit looser, so it's a less tightly bundled aggregation pattern. We could also set this equal to some modulo value. So let's say gen modulo, and we could use a large number here as well and say modulo 17 equals 1. Or, we could say equals 6. Or let's do 5. So 5. Now, if this first condition is not met, it's going to jump to this second condition, which occasionally should be met, and we can check this. When we start getting these more complex values, it's a little bit harder to conceptualize. So we could kind of do the math and make sure that we have minimal overlap, but surely at some point, because multiples, we will get some overlap between these conditionals. So let's go ahead and print second condition. It can be really anything. We just want to give ourselves some note that says, like, did this happen or not? Is this actually working how we might expect? So second condition, hit play. Okay, it looks pretty close, but it looks like right here, that condition was met and our hinge has widened even more. And if we decrease this number, so let's do every 11th step, we could keep that as a remainder of 5, or we could change that value as well. Let's just keep it as a remainder of 5. So every 11th step, which is going to occur now, every 11th step happening at the generation where the remainder divided by 11, the remainder is where the generation divided by 11 gives us a remainder value of 5. So if I hit play, we now should see whatever that adaptation to the aggregation was happening more frequently. And you can see that it happens so frequently now that we actually get these kind of tight spirals happening inside of our aggregation pattern. So if we want to keep that loose, then we actually need a larger value here. We can hit play and then play that again. We want to try and look for primarily patterns without self-intersection so that they can actually relate to a buildable assembly. Now, it doesn't mean it's a structural assembly, but it means that it's possible to be stacked without those self-intersections. Okay. So the next thing that we can do with these recursive functions, and this is where we kind of really get into exciting territory, is we can start to compound these actions through what's called branching. So with branching, all we're doing is basically saying, once we create one, on that one we created, we want to create 2. So for each one we create, we want to create 2. Now, since this is a kind of exponential increase in the output, you always want to start with a low number of generations. So let's say 4. And then I'm going to copy all of this, and then we're going to comment this out, because we're going to mess up our existing code quite a bit. So I'm going to paste that down here. It's the same exact code that we just had. We have a generation value of 4 being fed in. We're subtracting that each time, which is great. Okay, and now what we want to do here is first we'll just start off with for every single time we orient, instead of making 1, make 2. Well, we can just do that fairly simply by nesting inside of here, not just orienting one object, but orienting 2 every single time. So we can say face index, and let's say face index 1 equals 0, face index 2 equals 1. And then now we have to say surf1, face index 1, and we're just adjusting all of these values so that for every 1 we make 2. And this can be surf1, corner points 1. Then we want to copy and paste this so that, again, for every 1, we're making another one. Reference is going to be reference 1. Reference 1, we can copy corner points 1. Okay, and then new polysurf 1. And we want to move our delete surfs down slightly. And then we're going to copy each one of these. So we're going to copy the reference and target. And we're going to make these ref2, target2, and copy our corner points into each of these corner points variables so that we're grabbing those corner points instead of our other face. So we now have basically 2 faces being selected. And then lastly, we can just orient twice. And we're going to call that new polysurf 2, reference 2, target 2. So now when we do this, we're going to be orienting 2 different objects. And now we have our new polysurface being fed into our recursive aggregation function. So if we actually have 2 instead of the 1, what we could do is we could take each of these 2, pass it in there, so then we need another function that we can pass in our second value. That way we can use each one, and we'll go from 1 to 2, 2 to 4, 4 to 8, and so on. So if I hit play, we can back up and then select our tetrahedron. And what we should see with this type of pattern is a certain degree of symmetry. It looks like we also have self-intersections happening here, but we do see that degree of symmetry as they kind of branch away from each other. So for every 1, we have 2 being made. Now if we change the face index for each one of these 2, so instead of 0 and 1, we can do 0 and 2, and then hit play. Again, we get a certain degree of symmetry, eventually with a collision there. Now we can try 0 and 3. And here we get a kind of total separation and a more linear pattern. But there is quite a bit of self-intersection or duplication. Instead of doing this every single time, we may just want to do this branching operation under certain conditions. So we may not want to do this all the time. Instead, we may want to only perform this every 6th step, let's say. So if that is the case, we can go ahead and let's do index 1 and 2. I think those are faces next to each other here. So let's do index 1 and 2. We want them to be next to each other so that they kind of branch out. And then I'm going to say let's only use those, and let's only do this kind of doubling function every so many steps. So if underscore gen modulo 7 equals 0, or we'll do 6, so that it happens at the end of the steps and not the beginning. Because when we start with a value of 0, then if our remainder is 0, the first time we do it, we're going to branch. If we don't want to branch immediately and we want to delay that branching, we just need this value to be, anything but 0. Now we can enter in all of these values. We can also tab in these as well. And then we can say under all other conditions, so else, and we'll just have the same setup that we had before. So I can actually just go up here and we'll copy the code that we had here, including all of our modulos inside of it as well. So I'm going to copy this and then select all of it, uncomment, and then tab in one time. So else, and then we say if this one condition is met now, change face index to 3 and then 1. I'm going to delete this print second condition statement. We don't need to check that anymore. And then we now have that face index being used, constructing the corner points, constructing our references, orienting, deleting the surfaces, and then aggregating. And then we're using that new poly surface. So under most conditions, we're just going to be making one new object. And then under a certain condition, which is when the generations divided by 7 gives a remainder of 6, then we're going to be branching and adding 2. And what's interesting is when we branch, we actually create 2 separate downstream aggregations, meaning each one of those items can then start to grow, and then they branch, and then they grow, and then they branch. And we'll start to see how this impacts the aggregation set when we hit play. So if I hit play, select this. Okay, so we only have, I think, 4 generations there, so we're not doing too many. So let's try 40. Hit play, and then select our tetrahedron. There you go. So you can see a lot tighter aggregation being made. We might want to even change the face index. We could change those either in our conditional statement in general. What if we just say, so if I want this to never run, I could just make it an impossible value like 12. It's never going to be 12. So I just want to double check again that our typical condition is linear. So I'm going to hit play. Okay, so this looks good. This is a nice linear pattern. So that's going to be fine. So then if we could come back here, we could make this happen less frequently. How about every 21 steps with a remainder of 12. Let's try that. And then face index 1 and 2. Could also try 2 and 3 or 3 and 2. It doesn't necessarily matter. So let's hit play and then see how this works out. So it should happen significantly less frequently, that branching pattern. If we type cell duplicate, we can see where it actually overlaps and kind of feeds back into former positions, which can happen in these aggregations. But it looks like we're getting symmetry here. So this is our center object right there. Looks like we're kind of feeding up and then back down maybe. And we have some kind of diagonal symmetry right this axis here. So I think if we let that run even longer, we would see that play out. Let's try 120. And we would get a clearer picture of what that branching is actually doing to our larger aggregation structure. Yeah, so we're starting to see those streams kind of emerge. Now, what if we give it even longer? So 120, let's do 280. Maybe I'll start with a little bit less. Let's do 240. 240, and instead of every 21st, let's do every 43rd with a remainder of 12. Or, yeah. Hit play, select our tetrahedron, and let it run. So we know that the pattern is generally linear without the branching. So now with a longer step, and until we get to the branching pattern, we can see it performing linearly and then basically splitting into the branch. So we see several branches starting to emerge, where then it goes back to its linear pattern. Anywhere that you see a kind of bundling and then split into several different streams, like we see here, so we see a stream kind of starting here. That's actually a branch from our branching pattern, calling two different functions with two different objects, or rather the same function twice with two different object inputs, and then creating branches from there. Instead of watching them draw out, now that we have a kind of grasp on what this is doing inside of Rhino, if we want to hide the preview of every single step and instead just let it process as quickly as it can and then just look at the output, what we can do is go all the way to the top of our script and we can say rs.enable redraw, and we can set this equal to false. This is going to tell Rhino, don't update the viewport. We don't want to see you computing each of these different iterations. We just want to see the end. So first, this command says, don't draw it into our viewport at all. So then at the very end, we need to copy this same exact command. And we need to go somewhere below whatever we're running and say rs.enable redraw true. And that tells it, okay, we've now done all of our computations. You can now redraw the viewport. So if we zoom out a little bit and then hit play, instead of stepping through and getting it loading all the time, we can just hit play, select our tetrahedron, and it takes a significant amount less time. This works with a base tetrahedron object, but if we wanted to actually aggregate not just a tetrahedron, but a tetrahedron with another type of object, what we would have to do is not just select our surface, but select which object we wanted to reference. These types of aggregations can be based on certain aggregating logics or growth logics like Lindenmayer systems. So I won't cover it in this particular video. I might cover it in a future video discussing how we can use Lindenmayer systems to create decision trees, and also to be able to use multiple different types of objects like tetrahedrons and octahedrons combined together, but also use those Lindenmayer systems to control how we're selecting our faces, how we're selecting our objects, and our branching patterns. If we just look briefly at this description of Lindenmayer systems, we can look at the description itself or example outputs. Essentially, they approximate kind of growth patterns in many plant structures, which is a byproduct of those plants spawning new particular branches like we did in that aggregation example. But they come in several different flavors of how this kind of branching occurs. So the most basic is going to be just two variables, an A and a B, and essentially the rules are that if the item is A, then branch to AB, and if the item is currently B, then branch to A. Now, I'm going to kind of put a pause on this for now, because when I'm just discussing functions, I don't typically like to get into L systems. I think L systems are a lot easier to write with something called a class structure. So that's going to be the next series of videos that we cover, where we can actually store certain properties like what class, let's say, whatever you'd like to call it here, each one of these objects are. So what if we have an A and a B, so that's an octahedron and a tetrahedron, and we knew that every time we had an octahedron, we wanted to create two tetrahedrons on two particular faces. Well, we could structure these rules very similarly and say, okay, let's take this octahedron, let's branch to two tetrahedrons, and then let's take maybe all three of them, and let's move them all in a certain axis, and then at a certain point, let's turn it, let's do a different orientation, let's do whatever, and we can actually structure our own L systems or create our own rule of aggregation logics or growth logics, very similar to the way that these are starting to be laid out. But this is much easier when we get into the idea of classes and being able to embed properties or store properties within each individual element. It is possible, I suppose, to do with just with just clever management inside of functions. But again, I personally prefer to do it inside of class-based structures in Python. That's all for this last exercise video on functions in Python. Again, there's a lot of versatility that these carry with them, so I highly encourage you to explore them, and even if it's just as simple as going through this aggregation example and really digging into testing different face indexes, different steps, different conditionals. Instead of branching once, how do you get it to branch 3 times? How do you get it to branch 4 times? How do you get it to branch twice under a certain condition and 3 times under a different condition? Or start to look at 2 different types of objects. How would you even conceptualize that? How would you integrate that into the example that we've gone through in the last several minutes? So I'm going to leave it there for this video, but again, I encourage you to explore more independently, and in later videos covering classes, we'll get back into similar structures and start thinking again in a similar logic as we've done in this video.